So let's talk about the tides. In this explainer, we're going to uncover the incredible cosmic dance that creates the constant rhythm of our oceans.
I mean, if you've ever stood on a beach, you've seen it. This constant, predictable rise and fall of the sea. It's one of the most powerful and reliable forces on our planet. So what's really going on here? Why does it happen?
Here's what we're going to cover. First, we'll look at the basic pattern. Then, we'll introduce the main culprit. After that, we'll solve a really cool puzzle, bring in another major player, and then see why it all looks so different depending on where you are in the world.
Okay, first things first. Before we get into the why, let's just lock in on the what, the fundamental rhythm that we can actually see and experience along any coastline.
Yep, 2. That's the magic number. In pretty much any 24-hour period, most places on Earth will see the ocean rise for a high tide, fall for a low tide, rise for a second high tide, and fall for a second low tide. It's this incredibly consistent cycle. But what's the engine driving it?
So what is the force behind that rhythm? Well, to find the answer, you have to look up. The main character in our story, the #1 driver of the tides, is our closest celestial neighbor, the moon.
And it all comes down to one fundamental force: gravity. You know, that pull that exists between any two objects with mass. And the strength of that pull really depends on just two things: how much stuff the objects are made of, and how far apart they are.
Now this part makes perfect sense, right? The moon is close enough that its gravity is constantly tugging on our planet. And because water is a fluid, it responds to that tug by piling up, creating a bulge. And that bulge is our first high tide, right on the side of the Earth that's facing the moon. But hang on, this only explains one of the 2 high tides. Where does the other one come from?
And this is where things get really interesting. This question actually stumped scientists for centuries. If the moon is pulling the water towards it, how in the world do you get another high tide on the other side of the planet?
This is the absolute heart of the tidal mystery, because it feels totally backward. You'd think the water on the far side would be at its lowest, not its highest. It's not some strange anti-gravity effect. The real answer is actually way more elegant. The key is something called differential gravity. It just means the moon's pull isn't the same across the whole planet. Think about it. The moon pulls hardest on the ocean water closest to it. It pulls a little less hard on the solid body of the Earth itself, and it pulls weakest on the ocean water on the far side. So what happens? The whole planet gets stretched. The solid Earth is literally pulled away from the water on the far side, which gets left behind, creating that second bulge. So, here's how it all comes together. Imagine those 2 watery bulges are just sitting there, held in place by the moon. Now, the Earth is spinning on its axis once a day inside those bulges. So as your location on the coast rotates into one bulge, you get a high tide. As you rotate into the area between the bulges, you get a low tide. Then you rotate into the second bulge, high tide again. And finally, you pass through the other low tide area to complete this cycle.
Okay, so we've got the moon figured out. But the moon isn't the only object pulling on us. We've got our system's ultimate heavyweight to consider, the sun. Now you might think the sun, which is 27 million times bigger than the moon, would be the star of the show here. But remember, tides are all about that differential pull. And because the sun is so unbelievably far away, its gravitational pull on the near side of Earth versus the far side is almost identical. The moon, being so much closer, has a much stronger differential effect. That's why it's the undisputed king of the tides.
But the sun's influence is still a big deal. When the sun, Earth, and moon all line up, which happens during a new moon and a full moon, their gravitational forces combine and pull together. This creates what we call spring tides, which has nothing to do with the season. It just means you get these extra high tides and extra low tides. Then when the sun and moon are at a right angle to each other, their gravitational forces are fighting, partially canceling each other out. This gives us the much more moderate neap tides.
So, we have this really clean, beautiful theory of how it all works. But that brings up one last, really important question. If the physics are the same everywhere, why are the tides in the Bay of Fundy over 50 feet high, while in the Mediterranean, you can barely see them change at all?
Well, the simple answer is that our planet isn't a perfect, smooth, water-covered sphere. We have continents. These tidal bulges get disrupted and shaped as they move around the globe. The water has to flow through deep channels, around huge landmasses, and into bays. A funnel-shaped bay, for example, can dramatically amplify a tide, while an enclosed sea might barely feel a thing.
This quote just nails it perfectly. You've got this elegant, almost simple physics of gravity playing out on a cosmic scale. But the way we actually experience that force down here is a beautiful, messy, and incredibly complex local reality.
So we've gone from the beach all the way out to the sun and moon and back again. If you're going to boil all this down to one core idea to take away, what is it?
It's this. Tides are a gravitational dance between the Earth, Moon, and Sun, but that dance is choreographed by the local geography right here on our planet. It's a global phenomenon with a local accent, a grand celestial dance getting a very terrestrial performance.
And I'll leave you with a final thought to chew on. We know for a fact that the moon is slowly moving away from us, about 1.5 inches every year. As that distance grows, its gravitational pull will weaken. So what does that mean for the future of our planet's ancient daily breath?